Hello. We're pleased to introduce you today to our system, OmniTune. Database management systems are often posed queries which are used as decision support for high-stakes selection processes. While structures vary, these queries usually have in common a set of requirements about the result records. However, these requirements are usually specified approximately. We will now open our system, OmniTune, and use an example to see how it works. This is the OmniTune interface. For the following example, we'll use the law students database, containing a listing of law students from various regions, along with their undergraduate GPA and law school admission test scores. We want to use this database to decide how to divide a cross-regional scholarship grant. We'll act as a policymaker to decide the acceptance criteria for our scholarship. Let's start by entering our initial query. We'll now formulate our requirements, stating our performance-based acceptance criteria as LSAT score above 40, with UGPA score above 3.5. Let's implement our query accordingly. To explore the number and performance of qualifying students across regions, we want our query to group students by region containing each region's average UGPA, average LSAT, and count, where UGPA is greater than 3.5 and LSAT is greater than 40. When we're done, we can press Continue. On the right side of the screen, we see the original results of our query. Let's say we are not satisfied with our results. First, we'd like to raise the number of qualified students while limiting the amount of students from each region. So we'll require the amount of students from each region to be between 500 and 2,000. We also want to reduce the variability between regional amounts, so we'll require, for instance, the coefficient of variation between region sizes to be below 0.4. Lastly, to maintain similar performance levels between students, we'll limit the standard deviation between regional average UGPA scores to be under 0.05. Now we will let our LLM implement it as a legal Python function, so it can be easily used by our system. The system notes here in green when the LLM has finished generating the function. On the right side of the screen, we can view the LLM-generated objective function. We can see it implemented all of the constraints we requested, returning a mean between each constraint's deviations. This is our model's default behavior, unless the user specifies otherwise. The LLM is always instructed to return a score between 0 and 1. To change specific behaviors of the function, users can edit it as well. Let's move on to the next step, the refinement distance method. For the refinement process to generate a similar query to the original, we'll need to define which refinement distance evaluation method to use. Previous works mentioned in our paper define refinement distance in various ways. We have pre-implemented two of those functions ready to use, a syntax-based semantic distance and a result-based distance. Users can also define custom distance methods. Here we will use the semantic distance objective method, which examines the differences between predicate values within the where clause. We'll not proceed to our next step. Here we set a threshold for constraint satisfaction between 0 to 100%, where higher values mean higher compliance with the constraints. We'll pick a 90% threshold to allow a very limited constraint deviation. Now we can press Start Refinement. OmniTune LLM-based refinement engine now started working. Our solution builds upon the well-known actor-critic paradigm, adapted from classical RL, and includes two LLM-based agents, an actor and a critic. The actor explores the dataset using short Python queries and proposes SQL refinements accordingly, while the critic checks compliance against constraints and evaluates similarity to the original query. As our system has started running, we can see the current refinement, which currently is the original query. Below, OmniTune notes the current level of constraints compliance and refinement distance. We also provide detailed analysis for the current deviation from each constraint. For instance, the first refinement lowered UGPA threshold from 3.5 to 3.1 and the LSAT threshold from 40 to 36, and during the process, the system attempts to make sure constraints are satisfied to the required level, while maintaining low refinement distance within a predefined time budget. Here we see that OmniTune was successfully able to find a refinement after 4 attempts. The final query lowers UGPA threshold from 3.5 to 3.1 and LSAT threshold from 40 to 33. The constraint satisfaction score 0.09 means 91% overall constraint satisfaction, while the semantic-based distance from the original query is 0.29. We can go over the detailed description of constraint satisfaction to see that 2 of the constraints are satisfied. Region size is maintained between 500 and 2,000, and the standard deviation of average UGPA across regions is lower than 0.05. The coefficient of variation between region sizes is not completely satisfied, but at 0.51, it is close to the 0.4 threshold we initially required. Below, we see the difference between our system's final refinement and the original query results. We see that while it lowered the average UGPA and LSAT for each region, drops were minimal and scores are still high. On the size column, we can see that the refinement included between 500 to 2,000 students from each region, satisfying our size constraint. After the refinement process is completed, users can view the execution log using the Log tab, allowing a deep dive to the reasoning and explainability process of the system step by step. In our live demonstration, we will show additional refinement scenarios on different datasets, and we invite you to participate and send us your own examples of queries and constraints to try them on OmniTune as well. We look forward to being able to try OmniTune, and we appreciate your time. Thank you.